Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tear, and this is my continuing series on daily math problems that I post on the Facebook group Classical Mathematics. I haven't done one of these in a while, but I'm doing one now. And this was a pretty popular problem I posted about a week ago, and it was even modified by one of my friends, Otto Bretcher. I'll get into that. So the problem involves lunar orrery orbits. Anyway, let's begin. So here's the statement of the problem. Um, I'm going to read my slide here so I can see this. Yeah. So an orrery, such as the one shown on the right, is a model of a star system with planets orbiting a star and satellites orbiting another planet. Consider an orrery with a planet making a counterclockwise circular orbit of radius a about a star at constant angular speed, as well as a satellite orbiting the planet at constant distance b from the planet, with b less than a, also at a constant angular speed and within the same plane as the orbit of the planet, such that it completes exactly n counterclockwise sidereal orbits around the planet during the time the planet takes a single orbit around the star, with n an integer greater than 1. Okay, and I think I should mention what a sidereal orbit is. There's two different kinds of orbits. There's sidereal and synodic period. Sidereal just means that its orbits n times with respect to, if you like, the fixed stars, not with respect to the planet. That would be the synodic orbit, which is less than anyway, so for part A, I'm asking for the root mean squared distance with respect to time of the satellite from the star during its orbit. I had to change this. The original statement I probably asked for the mean distance. Turns out the mean distance is an elliptic integral, which is very difficult to calculate. So I modified, I changed the statement of the problem. Root mean squared turns out to be easy to calculate. So that's part A. Part B, I'm asking for necessary and sufficient conditions on A, B, and N for the orbit of the satellite not to cross itself. In other words, to be a simple closed curve. For part C, I think C and D are kind of tricky here. Part C, we're assuming the conditions in B are met. We want to compute the area enclosed by the orbit of the satellite as the planet completes a singular orbit. So we're going to get a closed curve for the orbit of the satellite because n is an integer and we just want to find its area. And then for part D, I'm asking for necessary and sufficient conditions for A, B, and N again in order for the orbit of the satellite to be convex. This is a lot stricter requirement than not crossing itself. Um, and this part was contributed by my friend Otto K. Bretcher, that I mentioned here. And by the way, you might be interested in knowing this, but the orbit of the moon around the sun turns out to be convex. Although I think all the other moons in the solar system have concave, or at least part of it is concave. I just thought I'd mention that. So anyway, that's a statement of the problem. So now we want to solve it, and first we have to set everything up. So I'm defining this vector r, which is the displacement of the satellite from its star, and we can write that as a sum of u plus v, where u is the displacement of the planet from the star, and assuming it's a circular orbit, so it undergoes uniform circular motion. I think most orreries are built this way. I've never seen an orrery that involves an elliptical planetary orbit. Maybe they exist, but I've never seen one. I haven't seen too many orreries, by the way. I think orreries were very popular in the 18th and 19th century, but I'd say they're pretty archaic these days. But anyway, so we have u, that's the vector corresponding to the planetary orbit, and that the x component is a cosine t, and the y component, that should be a, yeah, a, yeah. So a is a radius, and so it's just a, it's just circular coordinates. A cosine t is x and a sine t is y. I'm sure you guys are familiar with that. This is a formula for uniform circular motion, and t is sort of a scale time here. So t is actually um, um, the time in units of the period divided by 2 pi, if you like. So t is sort of the angle theta, if you like, the point makes with respect to the positive x-axis. And then v is similar. There's a similar equation for v. V is the displacement of the satellite from its mother planet, and the radius of that orbit is b. And again, we have this time since the satellite completes n orbits in the time the planet completes one. We see that v has x component b cosine nt and y component b sine nt. That just means it's orbiting n times as fast, the angular velocities n times. We'll do this for the planet. Um, and so to get r of t, we just add these two. Um, and we get for the x component a cosine t plus b cosine nt, and for the y component a sine t plus b sine nt. And and then I have pictures on the bottom. Say pictures worth 1,000 words. So um, I have three cases shown on the bottom here. For I guess for each of these three cases, b is equal to 1 and n is equal to 4. That means that the satellite is orbiting its mother planet 4 times every time the planet orbits the star once. Um, and I think you can kind of see what's going on here. We get three very different kinds of behavior here. So for the first case, when a is 3, you see that this orbit of the satellite does crosses itself 3 times. That means it goes retrograde during the times after it crosses itself. And then the second case, I think this is kind of the more generic case. This is a case where the orbit doesn't intersect itself, but it's not convex. There are places where it's concave towards the planet. So, and then the third case, when A is 20, in this case we do get a convex orbit. I think you can see that in this case. I mean, if you just look at the orbit of the satellite is very tiny compared to the orbit of the planet, so factor of 20 smaller. And the red in each of these three cases, the red circle, the dashed circle, is the orbit of the planet, and the blue curve is the orbit of the satellite. So these are three very different types of behavior, and we want to know when each of them occur. So anyway, so let's do part A first. So um, yeah, so part A is probably the easiest. All we have to do for part A to get the root mean square distance, we just have to first calculate the mean of the square, r of t squared. And that's pretty easy because we have formulas for x of t and y of t, we just plug them in. And you know by the Pythagorean theorem that r squared is equal to x squared plus y squared. So you just do the algebra here, and you get a lot of simplification. You get a lot of trigonometric simplification when you do this. The final result you get is a squared plus b squared plus 2ab times the cosine of n minus 1 times t. But now we're only interested in the time average. And I think the thing you should notice here is that this last term, cosine n minus 1 times t, I think you guys are all familiar with how sines and cosines look. If you go through a whole period, in this case n minus 1 period, the average value is 0, because cosine and sine are symmetric. Um, well, because of symmetry, the sine and cosine. So that the last term is going to cancel when we integrate, and when we take the average, and we're left with the average value of r squared is a squared plus b squared. And if you want the root mean square, average value of r, you just take the square root, and that gives the square root of a squared plus b squared, which is kind of nice because it's actually the length of the hypotenuse of the right triangle with legs A and B, if you want to think of it that way. Anyway, so that's part A. That was pretty easy. So what about part B? Part B is not too bad either. It's a little bit harder. You have to kind of know something about angular velocity. This is the way I did it. There may be other ways to do it, but um, we so what's true? We want to find the necessary and sufficient conditions for the orbit to intersect itself, and I think you should note that the orbit intersects itself if and only if at least part of the motion is retrograde. So I mean, let's just go back to a couple slides here. So I think you can see in the first picture on the left here, this is the case where the blue curve intersects itself. The reason it does is because when the satellite is closest to the star, it's actually going in the wrong direction. It's orbiting it clockwise rather than counterclockwise, and that's the only time this can happen. So so that means that um, we know that the orbit is doesn't intersect itself if and only if the angular velocity is always positive or always non-negative. And there's a formula for angular velocity. It's just the velocity vector dotted with the unit vector, which I'm calling theta hat. And that's just the unit vector in the theta direction. If you like, it's a unit vector going counterclockwise about the origin. Um, and we know from calculus, we know that the components, I think I wrote this down wrong here, should be minus sine t comma cosine t. I wrote it down right later. But anyway, so we can just calculate this. And well, we want this to be non-negative. And when you do the calculation and simplify everything, what you get is a plus nb times the quantity 1 minus 2 cosine of n minus 1 times t. And I think you'll notice that we want to minimize this. We want to find when the angular of t is minimum, could possibly be negative. And I think it's pretty easy to see here. The minimum value of the cosine term is minus 2, so the term in parentheses here, multiplying NB, is minus 1. So the minimum value is going to be A minus NB. And we want that to be non-negative, and we know that A minus NB is non-negative if and only if A is greater than or equal to NB. That should be greater or equal. You still get a curve that it has a cusp, but A equals NB. It has cusps, but it still doesn't intersect itself. It intersects itself if and only if A is less than B. And that was like I showed you in the picture earlier, the when n is 3 and when n was 4 and a over b is 3, you do get an intersection. So that's part B. That wasn't too bad either. And then part C. So now we want to calculate the area of the orbit of the satellite, and um, so we can use Green's theorem. This is a nice result for calculating the area of a closed curve in the xy plane. If you're not familiar with it, here it is. I think you can derive it using Stokes' theorem. There's different ways you can derive this formula of the area of a closed curve, but this is a nice formula. It's equal to 1/2 times the integral over the curve, I'm calling it C, of the quantity x dy minus y dx. And we can simplify this. We want to write this integral in terms of t. And if you do that, you just have the integral t going from 0 to 2 pi of xy dot minus x dot y, where the dots mean derivatives with respect to t. So that we can calculate. We can calculate the integrand. That's the first thing I'm doing here. and you get kind of an ugly expression, but you can simplify it using trig identities. And when you do that, you get a squared plus nb squared plus n plus 1 times ab times the cosine of n minus 1 times t. That's still kind of an ugly expression, but we're integrating this thing, t going from 0 to 2 pi, and we really don't care about the last term here because that integrates to 0 for the same reason I was talking about before, the average value of a cosine is 0. So, and then the integral, I think I left, yeah, and then and remember we have this factor of 1/2 outside the integral. So we're going to get 1/2 times 2 pi, which is just pi, times the constant term, which is a squared plus nb squared. So that's the area. I think it's a really nice formula. I mean, you can sort of do a sanity check on this when n is 0. It's just pi a squared. That's where the period of the it's really the case where the satellite's not orbiting at all. It just saves a fixed displacement from the planet. We know the area of the orbit of the planet is pi e squared, and the satellite in this case is just displaced. So that's pi e squared as well. And if it orbits n times for each orbit of the planet, you get an additional n pi b squared. You get n times the area of the orbit of the satellite around its planet from the point of view of the planet. There might be another way to prove this. I don't know. But I think it's a nice result. Anyway, so that's the answer. You can do it using Green's theorem, which is the easiest way I know. And then finally, we have one more part of this problem. This is probably the most difficult one. We want to determine necessary and sufficient conditions for the orbit of the satellite to be convex. And the way you do that is you can use a formula for the curvature. There is a formula for the curvature of an arbitrary curve in the xy plane. It's this kind of ugly formula, kappa, we usually call kappa. The reciprocal kappa is called the radius of curvature. Um, but anyway, I find it more useful to work with kappa. I mean, radius of curvature of a straight line is undefined, whereas the kappa is 0 for that case. But anyway, so here's a formula for kappa of t. It's x dot y double dot minus x dot x double dot y dot. There should be a y dot, and that's the x double dot. And then the denominator is x dot squared plus y dot squared is the power 3/2. We don't really care about the denominator. The denominator is always positive. But we do care about the numerator, x dot y double dot minus x double dot y dot. Again, the dot's missing here on the last y. And if you calculate this, you get this kind of expression, but then you can simplify it. And when you're done simplifying, you get a squared plus n cubed b squared plus n times n plus 1 times ab times the cosine of n minus 1 times t. Yeah, we want to minimize this because we know that the the orbit is convex if and only if kappa of t is non-negative everywhere. So that's also true if and only if the minimum value of kappa of t is non-negative. And the minimum value, I think you can see, occurs when the cosine term is minus 1. In that case, you get a squared minus n times n plus 1 ab plus n cubed b squared for the minimum curvature, and we want that to be non-negative. So we have a quadratic formula, quadratic inequality, like I'm calling this f of x. This is this quadratic polynomial, x squared minus n times n plus 1 times x plus n cubed. Now x is a over b. It's easier to work with one variable. So we want to know necessary sufficient conditions for this to hold. And this is pretty easy. I mean, it turns out that you can factor f of x as just x minus n times x minus n squared. And this is positive if and only if x is either less than n or greater than n squared. But we don't care about the case x less than n. That a over b less than n. That's a less than nb. And that was a case where the orbit intersects itself, and we're not interested in that case. So we can throw that one out. And then we conclude that x has to be greater than n squared, greater or equal to n squared. Remember that x was a over b, so that means that a is greater or equal to n squared b. So that's a necessary and sufficient condition for the orbit to be convex. And like I said earlier, turns out the moon's orbit around the sun is convex. Actually, I read this a long time ago. It's probably better to think of the Earth-Moon system as a double planet system. Because the moon acts sort of more like a planet than it does like a moon of the Earth. As far as I know, I think every other moon in our solar system has an orbit that's not convex about the sun, but the moon does. So anyway, I just think that's kind of an interesting fact. Anyway, that completes my video for today on Orrery orbits of satellites. So thank you for watching. Long live math, and I'll see you guys next time. Bye.